Roy G. Biv. Never eat sauteed worms. My very educated mother just served us 9 pizzas. Except since we got rid of Pluto, I guess that one can be short a little bit. To many very educated men just screwed up nature. Oil rig, or even Leo says grr. Now most of these things are mnemonic devices, or things that are going to help you memorize some things in science. But the important thing that I want you to realize out of this is that just because we have mnemonic devices, it doesn't mean that the order of planets was based on these mnemonic devices. No, rather what we've done is we have put together these memorizing devices to help us remember the order of certain things or to remember how to perform a particular task in science. The important thing, as always, is that nature does not conform to our understanding. Rather, what we do is we try and fit our understandings to what we observe in nature. So we're going to take a look at something that helps us balance and deal with oxidation and reduction reactions. And it's important to note that this is not the way that the reactions occur, but rather the way that we have come up with to help us balance these equations. So let's take a look at how we balance redox equations. Now first off, you'll have to excuse my voice a little bit. I am feeling a bit under the weather, so hopefully you can understand me as you watch this video. But let's quickly review redox. Now redox has 2 halves to it. We have the reduction half and we have the oxidation half. And what I want you to remember is that reduction is due to a gain in electrons through the course of a reaction, and oxidation is due to a loss of electrons through this same reaction. And so if we want to get into what oxidation and reduction means to in terms of oxidation numbers, because now we understand oxidation numbers, we can explain reduction as a reduction in oxidation number. So the oxidation number, because the substance is gaining electrons, is reduced, hence the reduction. If something is losing electrons, it's becoming positive, so its oxidation number is increasing, and we say that substance is oxidized. So ultimately, again, reduction is a decrease in the oxidation number, and oxidation is an increase in the oxidation number. And if we take a look at a really straightforward reaction involving solid sodium and gaseous chlorine, which produces sodium chloride, or what we commonly call table salt, this can be split up into oxidation and reduction as well. So first let's assign an oxidation number for sodium, and of course sodium and chlorine both being in their elemental state, we can assign both of them an oxidation number of 0. And if we take a look at the sodium chloride that's formed, we have a sodium cation, or positively charged ion, and we have a chloride anion, or negatively charged ion. And we can of course assign these according to those oxidation number rules that we have, sodium being +1 and the chloride ion being -1. And then if we wanted to take this a step further and split it apart into what we call their half reactions, we have an oxidation half reaction, and of course we can see that sodium is being oxidized. Its oxidation number is increasing, and it's increasing because sodium is losing those electrons. It's becoming less negative or more positive. Then the other half of the reaction is going to involve chlorine, because as we can see, chlorine goes from an oxidation number of 0 to an oxidation number of -1. So its oxidation number is reduced. It's the reduction portion of that because it is gaining electrons, gaining negative charge throughout this reaction, so it's becoming more negative. Now what I want you to notice is that there is a way to balance this out, because even though the number of sodiums and chlorines are equal on either side of this particular equation, there is something that isn't equal, and that is the charge. And so in order to balance out the charge, we need to put electrons on either side of the arrow to help us balance out the charge. And in an oxidation reaction, you're going to put electrons on the product or right side of the arrow. As you can see here, we need that electron to balance out that positive charge of the sodium cation. And in the reduction half reaction, you're going to find those electrons on the left side to balance out, in this case, the negatively charged chloride ions that we have on the right. So these are what we call half reactions. And in a neutral solution like this, you probably look at this and say, I can just balance this reaction by inspection. Why do I have to split it up into half reactions? Well, that becomes relevant to us when we put it under certain conditions. A lot of these reactions occur under acidic and basic conditions, or acidic or basic conditions, and so we have to consider other things that are present in the solution, like hydrogen ions and hydroxide ions. So the best way to take a look at applying these rules is to work through an example. So we can see here that the perchlorate ion and nitrogen dioxide react to produce the chloride ion and the nitrate ion. And I'm going to say that this occurs under acidic conditions. So that is something that we will have to take note of, and you'll see that as we work through this particular example. So the first thing that we want to do is figure out what's being oxidized and what's being reduced. Now, if you're comfortable with oxidation numbers at this point, this is the best time to use them. So let's go through, and I'm not going to spend a lot of time on this, but let's just go through and assign these elements their oxidation numbers. There's nothing really tricky here in assigning oxidation numbers for this particular example, so I'm not too concerned about this one. So we can see here that the chlorine is going from +7 to +5, so its oxidation number is going down. It is being reduced. We can see that the nitrogen goes from +4 to +5, so it is being oxidized. So our half reactions here involve nitrogen being oxidized and chlorine being reduced. So if we were to split this up, we could see that we would have our oxidation half reaction and our reduction half reaction involving those two compounds, or those two elements, and the compounds that they're involved with in this particular reaction. So what we're going to do is we're going to take a look at each half reaction, and we have steps for each one of those half reactions. So what we've done is we've split up the oxidation and reduction into two halves. If you're arranging this on a piece of paper for a note, or you want to prepare for a test or an exam or something like that, it's probably best to put it into two columns, one being oxidation, one being reduction. For both the oxidation and reduction, these steps will be the same. So you'll notice that we're going to sort of mirror these steps with our oxidation and reduction approach here. And the first step is very similar to all of the balancing by inspection you've done to this point in your science career, and that is you're just going to take a look at the non-oxygen, non-hydrogen, and try and balance those. So in the case, if there was one nitrogen on one side and two nitrogen on the other, you would be using a coefficient. That's a number that goes ahead of an atom or a molecule in order to balance out those values. So we're not going to worry about oxygen or hydrogen, as I said, but anything else, we balance that first. Now in our examples, for both our oxidation and reduction, they're both balanced, so we don't have to worry about that. And we'll move on to the next step, which is we're going to add water to balance out the oxygens. So obviously these reactions, being in acidic or basic solutions, are going to be taking place in water, so there's lots of water around for us to balance this out. Again, remember, this is not the way that these reactions occur. This is just the method that we use to balance these types of reactions. So the first step we're going to do is balance the oxygens by adding water. So I'm just going to take a look at our oxidation example here. We've got two nitrogen on the left, or reactant side. We've got, two oxygen on the left, or reactant side. We've got three oxygen on the right. So we need to add one water. Each water, remember, contains one oxygen to the left side in order to balance out the number of oxygen on either side, giving us a total of 3. And again, for the reduction reaction, you're going to do the same thing to balance out the oxygen. The next step is we are going to add hydrogen ions. And this step is important even if you're in a basic solution. The next process, or the next step in the process, is still to add hydrogen ions to balance out all the hydrogens. Even the hydrogens that are not in water, we're still using the hydrogen ions to balance that out. So again, in the case of our oxidation, we can see that the two hydrogens contributed by the water that we just added, we have to balance them out by putting two hydrogen ions on the right. Now, if the solution is acidic, we can continue forward to what I'm going to call step 6. But if the solution is basic, and this one is not, but if the solution is basic, what we would do is we would add hydroxide ions to balance out the number of hydrogen ions. So if we take a look at our reduction reaction, I have there 8 hydrogen ions on the reactant side. I would put hydroxide ions on both the reactant side and on the product side. So you're going to add hydroxide ions, 8 hydroxide ions on the right and on the left, in order to balance each other out. Because if you didn't put them on both sides, then again your equation would be unbalanced, and that sort of negates the whole purpose. So we're going to add hydroxides to both sides to balance them out, again, if it's a basic solution. Now what you'll notice is if you add hydroxide ions to hydrogen ions, those two things will react or will combine to form water. So anything that you add in terms of hydroxide and hydrogen, you're going to combine those things into water, and then you're going to reduce as necessary. And what I mean by that is if you had 6 water on one side and 4 water on the other, then sort of those 4 water molecules, they really didn't do anything, so you're going to reduce that 6 to 2, and you're going to eliminate that 4 on the other side completely. So then we move on to step 6, and step 6 is the same whether we were using an acidic solution or a basic solution. So we're going to use electrons to balance the net charges. Like remember, everything has to balance here, even the charges. So we're going to use electrons to balance out the charge to make sure that the charge on the left and the charge on the right are equal. And so in our oxidation, you can see that the left side or reactant side is neutral. On the product side, before we add those electrons, you can see that we have an excess proton, a +1 charge, so we're going to add that electron there. And again, you'll notice the oxidation gets the electrons on the right side or the product side, the reduction gets them on the left side or the reactant side. Now these electrons are important because they're ultimately what are going to help us balance this equation. So we have to come up with some lowest common multiple that are going to help us figure out how to balance these electrons. So since our reduction reaction has 8 electrons and our oxidation only has 1, we're going to multiply our entire oxidation half reaction by 8 so that the number of electrons on the product side or on the right side of the arrow is equal to the number of electrons on the left side of the arrow. Now why is this important? Well, if we take these two half reactions to combine them together in one total reaction that's now balanced under acidic conditions, we have to combine these oxidation and reduction half reactions. And in doing so, what we're going to do is we're going to put these reactions together. We're going to take everything that's on the left side of that arrow, combine it together. We're going to take everything that's on the right side of that arrow, combine it together, and then we're going to reduce anything that's sort of redundant. So if we take a look at our examples, we can see the 8 electrons that are on the left, the 8 electrons that are on the right. So we can almost picture that as those 8 electrons not really doing anything, not really participating in the reaction aside from balancing it out. And so we can eliminate those. Again, you will notice that the hydrogens are on both sides of that arrow. And so one side we have 8 hydrogen, the other side we have 16. So again, we can reduce that, eliminate them on the left side of the arrow and have 8 remaining on the right. And again, if you're keen, you'll notice that you see water there as well appearing on both sides of that arrow. And so we can reduce the total number of water to just 4 on the left. And then ultimately you can add all of these things up together and arrive at your total balanced redox equation or redox reaction under acidic conditions. Now I know this might look like a lot, and it might even be a bit confusing at first, but most things are when you learn them the first time around. But I promise you, if you practice this a few times, this half reaction method will become very straightforward because